introduce or try to reach the point where we will talk about neural networks as quantum states, okay? So that what we want to do is to have representations of non-trivial quantum states in terms of these neural nets that we introduced yesterday, okay? So before doing that, let me remind you of a question we had yesterday was, can we also, sorry, so let me introduce, so yeah, the question that we were interested in is, can we represent quantum states in terms of neural networks, right? Like as I just said. And so the answer is yes, and we will look into a particular Hamiltonian, the ground state of the toric code Hamiltonian. Okay, and so I'll start with the question that I got from you yesterday, which was, can we also classify this phases of matter that do not have an order parameter, and in this case, topological phases of matter which are not described by order parameters? So that was a question that I got yesterday, and then the answer was that that yes. So that and we looked at this phase of matter, the Ising gauge theory, okay, which had this Hamiltonian, which is defined on the square lattice. The spins are on the bonds of the square lattice, and we said that this theory, or this gauge theory, this classical Hamiltonian, had two phases, one which has classical topological order at t equals 0, and at high temperature is just the paramagnet, so all the spins are more or less random, okay? And we asked the question, can neural nets classify this snapshots of the phases at 0 temperature and at an infinite temperature? And we said that for instance, that one of this was a ground state and the other one was a high temperature state, and that it was a much harder task to classify. And that the feed-forward neural network, such as the one we saw yesterday, was unable to classify these phases, okay? And then I said quickly that we would be able to use so-called convolutional neural networks to be able to classify those images accurately, okay? So what I'm going to be doing is I'm going to start describing what convolutional neural networks are, and then later on I'm going to be able to, I'll try to show that we can represent the ground states of an extension of this Hamiltonian. So this is a classical theory, or a classical spin Hamiltonian, and we'll make it quantum, and that's called the toric code, and we'll try to represent the ground states of that Hamiltonian in terms of a convolutional neural network, okay? So now I'm gonna go and try and use the blackboard, because it's better, hopefully, for everybody. So let me switch to the blackboard. Okay, so I'm going to discuss convolutional neural networks. And I'm going to motivate it with a simple examples using feed-forward neural networks, right? So suppose you have an image, right, that's very large. Suppose it's an RGB image, right? Like, so it's pixels in 2 dimensions, and then there's a third dimension, which is the color of the image, okay? So this is an RGB image, and then this will become our input to the neural network, let's say, okay? And so this input will be passed through a layer of a fully connected layer, such as the ones we were discussing yesterday, okay? And so we'll have some sort of neurons here and some activation function, and this image is going to be, I don't know, 200 by 200, and then this dimension is 3, the different colors in the image, okay? And then say we have 1,000 units here, okay? So so this, if I like, let me remind you how this, like each of these units in this hidden layer of the neural network work. Like we had a unit, and that unit took inputs x1, x2, and x3, and they have parameters w1, w2, and w3, okay, plus some bias. And what we said is that the output of this neuron, H or Y, doesn't matter, was some sort of nonlinearity, W understood as a vector transpose times X understood as a vector plus some bias B, where X is X1, X2, and X3, okay? So that's the output of this symbol neuron. But now our X is gonna be an enormous array of numbers, and it's gonna be, we're gonna flatten it and we're gonna convert it into a vector, and this vector will have a lot of components, right? Like it's gonna have 200 by 200 by 3, okay? Okay, and so each of these numbers will be fed to each neuron, right? And so on and so forth, and then every single point of this will have a corresponding W, okay? So that means that we'll have a matrix W characterizing the entire layer, which is composed out of, so you'll have a matrix or a vector for each of the 1,000 units, and for each of the 200 by 200 by 3 inputs, right? That means that the number of parameters in this layer is very large. It's exactly 200 squared times 3 times the number of connections we have per variable, right? So that's times 1,000, which is basically, or it is 120 million. Okay, so that means that the number of parameters if we want to process an image, and even a small image, so what you have on your phone is just way bigger when you take a picture, right? So if you have such an image and you want to process it through even just one layer of a neural network, you'll need to use 120 million parameters, and you'll have to train those biases and those weights, and so that becomes very computationally expensive, okay? Oh, sorry, yes, 1,000. That's right. Okay, so and then the other, so that's one drawback, right? That we have a lot of parameters. And suppose this weights, this big 120 million parameters learn to distinguish, I don't know, for instance, some digit in the image, right? And so it learns and it captures, say, these dependencies and so on, and it learns to distinguish trees and so on. But then suppose now that this 3 is shifted, right? So now these weights that before were acting on this number will not be, and this layer will not be able to distinguish that number anymore, okay? Because it's shifted with respect to the original position it had when it learned, okay? So then, so that's also a drawback of this type of neural nets, and so, and it's the two like these two drawbacks, the fact that you have a lot of parameters, and the fact that this architecture would be prone to distinguishing things at a fixed position are the reasons why we introduce convolutional neural networks, and they look like this. So, so we want, in the architecture, we want that that the same sort of features are useful to analyze parts of images in different locations, okay? So, so let's say analyze features everywhere in the input. For instance, when you use image processing, you want to distinguish edges, corners, contours, or parts of objects, right? Like, so things like edges, contours, etc. Okay, and we want this neural network to learn these features or these weights, and we want this to apply to all the like regions in the image. Okay, so we want that these features or these characteristics are detected or analyzed anywhere in the image. Okay, so then the question is how to achieve that, right? And that's what the convolutional neural network does. And let me tell you quickly what they are. Okay, or so remember that we started with feed-forward neural networks that look like this, right? Like where, if you want, let me do it in a one-dimensional, sort of a one-dimensional example. So we had 5, and then 3. So these are the inputs, okay? And then we said that they were connected to all the units, right? And so we had this, and also this, and this, okay? So all the inputs are connected to all the outputs, okay? And so we said that was expensive, but then what we're gonna be doing is we're gonna be making local connections, right? Like, so so we'll go from this to, say 1, 2, and 3. And so we'll connect only locally, what's spatially locally to, for instance, we'll connect this one, and this one, but not these two. Those two are, say, far away in space, okay? And similarly, we'll connect this one to this, and that, and this one, and this one, and this one, okay? So what we're effectively doing is we're removing all this number of parameters, right? Like when we're removing these connections, what we're doing is we're setting a bunch of weights to 0 in a way that you respect the dimensionality of the system, okay? So that's the first thing we do. So each hidden unit, say I, looks only locally at a few inputs, okay? So that's the first thing. So in this case, we went from 5 to 3 connections per unit, and by doing that, we save space and we save memory, okay? Then the other thing we do is we still have a bunch of parameters, but we want those to be able to detect patterns in the input, which are located everywhere in the image or in the input, okay? So what we do is we do one more thing, okay? We say 1, 2, 3. Let me, again, 1, 2, 3, 4, 5, 1, 2, 3. And what we do is now so let's see if I have different colors. I have only one color or two. So we'll do this, right? Like, so we'll connect this one here, and we will connect this one here, and then there will be a third parameter. And then when we move to here, what we do is we connect this one with the same parameters, right? And this, sorry? We can, yes. I'll explain the color in a little bit and how they work and how we use them in physics. So there will be details about it. Yes. Yeah, it depends on the system you're trying to study, and ideally you should respect the locality of the system, right? Like, for instance, if you're in 2D, you know that, for instance, in a lattice, right? You know that these points are near to each other, right? And so you try and encode that information you have about the system in the architecture, okay? And we'll have an example. So when we study the toric code, we'll have a two-dimensional lattice, and we'll use the fact that the spins are located in a two-dimensional lattice, and we'll use that information to define the connectivity of the network. Mm-hmm. All right, so then let me finish this here. So we'll have this connection here, this one, and this one, okay? So in such a way that if we detect, say, a pattern in these three, say, spins or in these three inputs, then this pattern can be recognized, whether it is here in this three, whether it is here or here, okay? So then by doing that, what you're doing is you're tying the weights of the neural network, okay? So those weights appear here, and this connection, and they're always the same. And so you're reducing the number of parameters, which initially was very large, and you are reducing them because you cut on the number of connections, but also because you tie the weights. So you have these weights acting on different parts of the input or in different parts of the image. Okay, so that's the idea with convolutional neural network. Okay, and so let me just be a bit more precise now. So what's a convolution? What's a convolution operation? Okay, so let me tell you about that. So in 1D, so convolution operation, and we start in one dimension. Okay, so suppose you have two arrays A and B, or two vectors A and B. So the convolution operator or the convolution operation will look like this, right? A, B, and we'll have component T as this expression here. So it's a sum over T or tau of A tau and B T minus tau, okay? So it's basically a shifted dot product, if you want, okay? And let me try and draw how this looks like in a particular example. So suppose you have let me see. So let me do it again. So A B tau sum over tau of A tau B T minus tau. Okay, so graphically this looks like this. So A, so let me do a tiny example. Okay, so it's going to be my A has a input. So this is 2, say minus 1. Do it a little bit higher. 2 minus 1 and 1. Say 1. And B looks like this. So it's 1, 1, 1, and 2. So these are the components of my vector, 2 minus 1, 1, and 1, 1, 2. And so the convolution operation looks like this, right? Like, so you take 2 from this 2, you multiply it by, so now I'll have this vector here. So 1, 1, and 2. So 1, 1, 2. And let me And then we have -1, right? So -1 times, and now we take this vector again, but now we shift it by 1 with respect to this original vector here. Okay, so now it's going to be 1, 1, 2, just shifted with respect to this original vector, and that's why, because we have this minus tau here, or that shifts vector B. Okay, and then finally we have 1, right? And it's shifted 1 more time, so we'll have 1, 1, and 2. And then we sum the whole thing, okay? So you have 2 times 1, and then 0, 0, 0, then you get what? You get 2, okay? That's too big, let's say 2. Then you have 2 minus 1 plus 0 is 1. Okay, you do then 2 times 2 is 4, minus 1 plus 1, that's a 4. Okay, and then you have 0 minus 2 plus 1 is 1. No, sorry, this is 2, so it's minus 2. Yes, minus 1. And here I have 1. Oh, sorry, 2, right? So this is the output of the convolution, right? Is that clear? So this one here. So it stands for the position in this new array that you created. So it's basically T labels each of these outcomes in the convolution. Okay? So that's the output of the convolution, is a new vector with indices T. Okay, sounds good. So that's how it works, right? Like, so we apply this convolution operator. That's how we write in terms of the expression, this operation here. And this filter, so I don't know, you can imagine your input being A and your filters being B, or your features being B. And then what you're doing is you have your input here and you're translating or processing it or multiplying it by this filters locally. Okay, so that's the idea. All right, you can do the same in 2D. Of course, so that's the definition in 1D. In 2D, it's a definition. It's analogous. So let me do it quickly. So in 2D, it looks like this. So A. So now these are matrices, for instance, and B. And now you'll have indices I and J, and you'll have now two sums. S sum over T of A, ST, B, I minus S, J minus T. Okay, and you can repeat the same geometric argument with this. And I have one example here. I don't know if, let me see how I'm doing it with time. So maybe I'll skip the 2D example, but it's basically the same, right? Like, so what you do is you have some sort of input A, and you have some, I don't know, some number here. And so this is, I don't know, suppose you have, well, any number here, set of numbers here, and you have 1, 2, 0, and minus 1. And what you do is you start with 1, and you'll have 1, 2, 3, 4. And the matrix that you have here, like for instance, 1, 3, 1, 0, minus 1, 1, 2, 2, minus 1. So first you'll have it here, right? Like 1, 3, 1, 0 minus 1, 1, 2, 2 minus 1, and then you have it times 2, right? This is this 1 here, this is this 2 here, and you'll have a similar thing here. But now the matrix is going to be shifted, right? It's 1, 1, 3, 1, 0, minus 1, 1, 2, 2, minus 1, and so on and so forth, right? Like you do the 4 different shifts, and you multiply them by the components, and then in the end you sum all this up, same way as we did there. It's only you do it in this matrix form. Okay, but in essence, it's the same operations. You generalize it to 2 dimensions. Okay. All right. So now, so that's the convolution operation. Now I'm going to discuss a little bit the question about the channels, right? Like, so what happens? So here I didn't have any extra channels and any colors in the image and so on, and so let me discuss that quickly. So what happens? So when you have multiple channels and multiple filters or multiple convolutions or multiple filters that you're going to apply on the image, okay? Filters and so on, okay? So what happens is the following. So we're going to go from this, which was what we were doing when we were doing a single channel or a single input in the image. And suppose now that we have, instead of only one channel, which is the example that I had here, now we have 3 or k of them, okay? So then what we'll do is we'll sum over those, okay? So we'll change this by a sum over the different input channels in the image, let's say, and we'll do a convolution with the filters or filters W or B, and we'll apply them to. We can have different ones for different channels. Okay, we'll have different filters for different channels, but then we can have each channel can be assigned to a set of output filters as well, and so we'll add this kj indices. Okay, and so this output, I'm going to call it I don't know, kj. Okay, that's just a name, and then so it's a set of j matrices that are the output of the set of operations or these convolutions. Is that clear? Or? Okay. And yes, so remember that we had this example at the beginning, and it's how your phone takes pictures, where you have an image, and it's a 2-dimensional array, right? But then the way they encode the colors is by having three different images, right? Like, so it's as if you have this 2-dimensional array, but now you have a 3rd dimension, okay? And this dimension can be, in the case of what happens in our phones, is 3 different channels, red, green, and blue. Okay, so an input image, on top of having this 2-dimensional structure, this matrix-like structure, it has an extra dimension k. Okay, and then that k encodes the different colors in an image. Mm-hmm. Any other question? Yep. Yes, so it's in the case of images, it's 3. In physics, we may have different things, and I'll show you one example. Mm-hmm. Yes.
Are there any case where you want to have a convolution filter that could like act on three channels at once, or it's not something that's done?
You could do it. You could do it, and in which case you would apply the same on each of the layers. So you can do that. I have never seen it before, but you can certainly do it. Okay. Okay. So that's the idea. So the last ingredient is how do we apply the nonlinearity? So I've explained what's a linear transformation, namely the convolution on the input, A, or A sub k, okay? And then what we do is we apply a nonlinearity O on the output, right? Like, so we'll have some nonlinear activation functions, such as the ones that I described yesterday, applied element-wise on the output of this filters, okay? And this is called a convolutional layer, okay? This entire convolution followed by application of a nonlinearity on top of the linear transformation, okay? So this is the so-called convolutional layer, okay? So let me go back to the slides to show you how using this yes. Sorry, I didn't get the question. With B in here, after, no, you have convolved the image with B or with W. So I changed the notation here. So B, so I replaced it with, so when I was talking about B, I was using just the one channel. And then I replaced it with a more general object that I call W. But this could be, let me even maybe call it B, or a generalization of that original B. And I think I didn't scrub the notation in that case, okay? Yeah. Okay, so let me go back to the slides and show you how we can use this to classify those snapshots. Oh, sorry. Before doing that, let me show you how these convolutions look like when you apply them to an image, okay? So here's an image of Jeffrey Hinton, the godfather of deep learning. And here we have a filter W, or B, sorry, we're using B here. So this is the original image, and then you convolve it with this, and see, so this is what the outcome looks like. So it blurs the image. And it's basically, what you do is you are averaging over the patches in the image, okay? And when you average, the edges kind of like get blurred, okay? And so you get this blurring effect when you do this convolution. So it's a weighted average, or blur, it's called. So this one, what do you think it does? Does it blurs, or does it sharpen the image? Yeah. Yeah, that's the right way of thinking about it. So it's kind of like sharpens the edges, okay? And it's because you can think of this filter as, when you apply it as the original image plus a Laplacian on the image, okay? And so there's, like, the Laplacian kind of detects sharp changes in the image, and so this one produces this sharpening, okay? You'll convince yourself. So I'll give you the slides and you think about it, and you'll convince yourself. So this one is, it's also interesting. It's an edge detector. So it's kind of like just the Laplacian of the image without adding the image. So if you take the image and you add this, then you'll get the previous image. And so this one detects edges, Okay, this one computes a gradient. So this one computes a gradient along the x direction of the image, so in this direction, and so you detect the biggest changes in the image. Okay, that's what it looks like. And so, as I said, when we take this this filters, different filters J, and we apply them on the image, on the original image, we get this different processings of the image. Okay, and then so these are examples of convolutional filters that you see in modern or relatively modern convolutional neural networks, and what they do is they detect patterns like these edges and patterns, and the edges can be found in different directions in the images, in natural images, and so on. And so that's how they look like in practice. Okay, and there's going to be an analogy when we do it with these problems in physics. And then we apply a nonlinearity, and so in this case we had this rectified linear units that I explained yesterday, and so you start creating this processed features OJ. So these are the OJs in a convolutional neural network, right? So this outputs here. Typically, on top of that, there are pooling layers which I will not use in the physics example that I have, so I won't explain them. But they're basically you take regions in the image, and then you take the maximum, for instance. So that's called max pooling. So out of the Z1, Z2, and Z3, you select the maximum of the three, and then you call it the output, Y. Okay, and that also reduces the size of the image and blurs, because you're replacing by averaging or by using a max, and that's a layer that I'm not going to be using, so I won't discuss it. But a full convolutional neural network is usually, okay, the input, the different filters, a nonlinearity phi, a pooling layer, which we won't have in the examples, and then you stack those, okay? You pile them up, and that's how you get this powerful neural network models, okay? So, so that's it. So now back to the gauge theory, right? So we had this, this problem of classifying this complicated, so let me see if I can go back. So we wanted to classify this either as a ground state or as a high temperature state, and feed-forward neural network couldn't do it. So then at some point we asked, can a convolutional neural network that can hopefully encode the law or the Hamiltonian of the system detect the differences between the two images, which is much harder to do in using feed-forward neural network. And the answer was that yes, that works. And so we use this, so these are our inputs, right? And we have a bunch of filters, right? Like, and the filters are only 2 by 2. And in this lattice, so let me show you how this lattice looks like, right? Like, so we have a square lattice that looks like this. Okay, so it's the usual square lattice, except the spins live on the bonds of the system. Okay, so they look like this. So it's a square lattice, except now we have the spins located on the bonds. So what that means is that it's the usual square lattice, but now we have how many spins per unit cell. So a unit cell is this object, right? It's this thing here. So how many spins are there in the unit cell of the square lattice? That's 2, right? Like, so you can think of them as 1 here and 1 here. Or you can think of them as a 1/2, 1/2, 1/2, and 1/2. But I'll take this approach, okay? And now, so when we are using this convolutional filters, what I'm going to be doing is I'm going to be understanding this as a usual square lattice, okay? And what we're going to be having is only 2 channels. And the 2 channels will be green and white, okay? So it's not like a RGB, it has only 2 colors, and the 2 colors correspond to the number of sublattices in the Bravais lattice of the system, okay? So this is where this is why I meant to explain the fact that we can have quote-unquote colors in this type of problems, okay? So this is how we do it. So we apply these filters. We have 2x2 filters, and they will act on the different sublattices, right? Like so our filters are going to be 2x2, and they will act independently on the green, on the green sublattices. So these filters will act in here, whereas the other filter will act on the other sublattice, okay? Does that make sense? Okay. So, and then if we construct such a convolutional neural network with, say, 2x2 filters, like I drew here, of 64 pairs of lattice, and this ReLU nonlinearity, followed by a fully connected layer, such as the ones I explained yesterday and at the beginning of today's lecture, you'll get a model that can classify those configurations with 100% accuracy, okay? So that was the idea. Now, how is this related to toric code, right? Like, so on its ground state. So let me start with giving you first an analytical understanding of what the CNN uses to make predictions about the model, okay? So importantly, so let me write down the Hamiltonian, the Hamiltonian of the system. So we have H is equal to minus J, sum over the plaquettes, okay? And the plaquettes are this here, so this one is a plaquette, this one is another plaquette, and so on and so forth. So each plaquette has 4 different spins, okay? And the Hamiltonian is such that you take J in the plaquette and you multiply the different spins, okay? So ground states of this Hamiltonian, you can imagine, are such that products over the plaquettes are what? Are 1, because we have this minus sign here, right? So that at low temperature, you gain energy from having what? This products over the different plaquettes to be equal to 1, or to be satisfied, or to be defect-free, that we say, okay? Is that clear? Right, so that's how these ground states look like, okay? So when we had this here, so the difference between a high temperature state and a low temperature state is that when you go and look at the plaquettes, the product over the 4 spins on every plaquette is always 1, whereas here you will see everything, okay? So that's the difference between those 2 images. And so you can imagine that if we wanted to go and detect every single one of those patterns, what you can do is you can go and effectively apply a convolution on each of the plaquettes and figure out if the plaquette is defect-free, or if it has a defect, or a monopole, as they call it, and depending on which community you come from. But this is a gauge theory, so there's defects when you have a product over spins on a plaquette, and you see a -1, then people call it a monopole, in analogy to the creation of a charge in that specific plaquette. Okay, so that's what the ground state of this object, or this Hamiltonian, looks like. A bunch of configurations such that products over the plaquette, products over the spins on a single plaquette equal 1. Okay, so that's the idea. And now, so what we did was we came up with an architecture with a very simple, yeah. Yeah, no, sigmas, so this is a classical Hamiltonian, so the sigmas are classical variables, plus or minus 1. I wrote it in terms of operators, because that's also doable. But for a classical system, in principle, they're just plus or minus 1. Mm-hmm. I'm considering the plaquettes in here. So it's this 1, 2, 3, and 4. And for this one, it's 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth. So those are the plaquettes I'm thinking about. Mm-hmm. That's not, that product is minus 1. That's right. But you can have white, white, black, black. So this is fine. Yeah. Mm-hmm. Right. There was one more question already. Good. Okay. Okay. So what we did is we came up with an analytical model for a convolutional neural network followed by a fully connected layer that classifies this perfectly, and we did it analytically. Okay, so let me show you. So this filters and the fully connected layer, and it gives 100% accuracy. Okay, so it kind of like works the way we intended, and it reproduces the problem exactly. And what we do and what we did is we thought about what would be the Boltzmann weight of this model in the limit of 0 temperature. So you'll have that the Boltzmann weight is a finite number when the plaquettes are satisfied, and it is 0 when when you find even one plaquette that is non-satisfied, that breaks this rule, right? Like this product rule. And so we took inspiration from that, and we constructed a set of filters. But before telling you the filters, what's the connection with, for instance, computer vision, right? So in computer vision, I mentioned that these filters detect edges and little patterns and so on. And so this is what you find when you train a convolutional neural network. Bunch of edge detectors, which I mean, people believe this is what happens in the actual visual processing system of our brain. That there's the first part of like our vision system, there's a bunch of edge detectors in our eyes, which is what you also find when you train a convolutional neural network. And then in our, like the analogies, instead of detecting edges, we detect this satisfied constraints induced by the Hamiltonian, okay? Or they detect monopoles or defects in these plaquettes. So this one is satisfied, but this one is not, right? Like it has the product is -1, and good. So let me show you what the filters are and why they work. Okay, so these are the set of filters that we use. So it's a bunch of them. Is A and B are the different channels, right? Like the green and white, or the different colors. And these are the ones acting on the sublattice A, and these are the ones on the sublattice B. And these blue ones detect only satisfied constraints. And I'll tell you why, right? Like, so let me draw one example here. Let's say here, one quick example here. So you'll have, let's say, let me see what I drew here. Yeah, let me draw a bigger example. So you'll have sublattice A, and A, and then B, B, A, B, and B. And so sublattice, the filters on sublattice B will act on this and then the ones on A will act on the spins. Okay, and so this cold filter, so you see they act, let's see if I can point out. So they act only on this vertical direction, 1, 1, for instance, and 1, 1 on the sublattice B. And so this is a filter that detects a satisfied plaquette where all the spins are pointing up, okay? So it's all this 1, 1, 1, 1, okay? And so why on A acts vertically? It's because of this, right? Like, so we're talking about a particular plaquette P, let's say this one here, and this vertical direction is just these 2 spins here, these 2, okay? Whereas on B, they act horizontally because they correspond to these plaquette, these 2 spins here, right? So, and so it means that as a pair, or as a little set, these 2 detect a plaquette which has all the spins up, okay? So the next one detects spins that are always down on that plaquette. This one detects 2 up and 2 down, and so on and so forth. And these ones detect, for instance, hot spin or hot plaquettes, where you have 2 spins, 3 spins up and 1 down, and so on and so forth. And that's how we constructed this convolutional layer. And then what we do with all this information is we pass it through a nonlinear activation. And this nonlinear activation is, it's a step function, okay? And it is a step function such that this filter activates, and this one activates, and so on and so forth. But then the last layer, which is passing all this information to a fully connected layer, what it does is basically it counts how many defects you have, okay? Or how many satisfied plaquettes you have. And then it uses the information of this plaquettes, the information about all the plaquettes in the system, and then it makes a decision, right? It tells you that looks like a cold configuration or a low temperature configuration. Whereas if you see one, even just one hot configuration satisfied, then it tells you that's not a ground state, okay? So this is how it looks like, or this is how it operates. And you can see this coded in this GitHub link if you want to play with it. Yeah.
This whole lecture you have been talking about the plaquette and that grid with the spins located.
Mm-hmm.
Is there any problem when you try to model more, let's say, 3-dimensional atom structures?
You can do it. Mm-hmm. You can do 3-dimensional convolutions, for instance. So the same picture that I drew here, you can draw in 3D, and you can apply the same concept and same ideas. Mm-hmm. Okay. Okay. Mm-hmm. So each of these filters will activate when you see this feature in the configuration. When you see a plaquette that's satisfied, the blue ones will activate, and when you see a plaquette that's whose product is not 1, you will see one of these activated. Okay, and then what this extra output layer does is to check. Okay, to check if you have only blue ones or if you have violated plaquettes. And then you will use this information to output either 1 or 0, okay? Through a second nonlinearity acting on the output layer. No, so I guess what we're trying to do is we're trying. So let me show you again the model we have. So we have this model, right? Like and this model outputs two numbers, right? So it outputs a number for the call neuron. It will be 1 if all the plaquettes, all of them are satisfied and the products are all 1. And it will be 0 if there's even just 1 for which the plaquette is violated. And the warm neuron will be the opposite, right? It will be 1 if there's even just 1 warm configuration, and it would be 0 if all of the plaquettes are satisfied. Okay, so that's how this output works. Okay, so finally, if I have yeah, this is an object that classifies 0 temperature versus yeah, we know the answer, right? Like what we're doing is, yeah, so we're not doing any finite temperature calculation here. This was just an exercise to motivate why we can write these objects in terms of convolutional neural network. And tomorrow what I'll do is I'll show what's the connection between this object here and the ground state of a quantum Hamiltonian, namely the toric code Hamiltonian. But this was just a toy example showing that convolutional neural networks can construct objects like this. Even though we know what the answer is, I'll hopefully try to show you tomorrow. Or maybe what I can do is I can give you a hint right now without introducing the toric code, but I'll give you a hint for what we will be doing tomorrow, or I'm not sure tomorrow, but in my next lecture, what we'll do is we'll get rid of the hot neuron, and so we'll have only one output, and then we'll have this structure, okay? And this, if we understand it as a wave function, so meaning that we can construct, say, a quantum superposition of these amplitudes given by this architecture that I constructed. If you make a quantum superposition of those, then what I'm going to argue tomorrow or the next time we talk about is that this, as a wave function, is the ground state of a quantum Hamiltonian in this case, and this ground state this Hamiltonian is called the toric code. Okay, so this is where I'm going. Okay, we did all these classification exercises of low temperature versus high temperature or infinite temperature configurations, only as a way to motivate the fact that we can construct ground states of many-body quantum Hamiltonians, such as the toric code, in terms of this architecture, this convolutional neural networks. So that's what I wanted to get to today, but I just didn't have enough time. I guess I was too optimistic. But so what I'll do next time is I'll introduce the toric code, what it does, how its ground state looks like, and then we'll conclude that these ground states can be written down in this form. Okay, and the motivation is that eventually, so we want to solve problems for which there's no solution, right? But the hope is that given the fact that we can write down some many-body Hamiltonian, so the ground state of some many-body Hamiltonians, that we can use neural networks more broadly for problems for which there's no solution. Okay, so that's where I'm going. No known solutions, exactly. Sorry, yes, exactly. No known solutions. Yes, yes. Questions. Yep.
So when you use convolutional layers, you pass like multiple convolutional layers simultaneously to the image in order to get different features simultaneously.
Mm-hmm.
Maybe not in a clear example, but on a broader example, you would use like multiple convolutional layers with different structures of these
Different matrices B, yeah.
So this is how the architecture can kind of work, like multiple convolutional layers to get more features.
Yeah, exactly. So, and that's indeed even in the toy model, right? Like, so in here, what we do is we have this different filters, right? Like, so we had the different Ks, which act on the different sublattices. But then we have different Js, which correspond to the different filters that we apply. And they correspond to, so in our case, so these are the different, the features you're talking about, right? Like, so we had 8 of those per sublattice, okay? So it means that J goes from 1 through 8, and K goes from 1 to 2, or A and B, right? So the structure of what we're using here is exactly this one, right? Like, it's exactly what you said, right? Like different features or different filters or different convolutions acting on the input, right? So it's exactly what you said, yeah. Mm-hmm. Yeah. Yeah, go ahead. Mm-hmm. Yeah, so in this case, our idea was detect only satisfy, like configurations where all the plaquettes are satisfied versus the rest, right? Like versus even configurations with just one violated plaquette. And for this, our construction works perfectly, right? Because we know exactly what the Hamiltonian is and what we're looking for. And what we do is we encode that information in the convolution, right? And so I'm not suspicious at all because it works 100%, but because I understand, right? Like so I understand in machine learning more broadly, a model that works 100% of the time may be not great because when you try it on some other data, then it usually fails because you're overfitting you're over optimizing. But in this situation, it's fine because we know exactly what's going on, right? Like we're exactly, yeah. Mm-hmm. You mean instead of? I think it's fine. Yeah. It, I mean, you change the like where you fill the numbers, but the numbers will be the same. If I understand correctly what you're asking. No, you shift the positions. Yeah. Um, I haven't prepared that, but I could. Yeah. Okay. Yeah. Yeah. Um, I can come up with something. I know. Oh, for the test, yes, I have prepared already. Yeah. Yeah. Exactly. So I'll come up with a problem. Mhm. Yeah. Um, you can use many things, right? Like it depends on your style, your taste, um, how comfortable you are. It depends on your problem, but I like all that I've done is usually using Python and some other library for machine learning, like for instance, TensorFlow or PyTorch or JAX. I've used all of them. It's really depending on the problem. Mm-hmm. I don't know if I answered the question. Yeah. Thank you so much. Yeah.